We continue the chapter Laws of Motion, and we were talking about in the previous video about the friction, different types of friction we studied. Now we discuss the work done against friction. Work done against a friction. The topic is work done against friction. So the first expression is work done in sliding a body. Work done in sliding a body. Work done in sliding a body over a horizontal surface. Over a horizontal surface. So we derive the expression for work done when a body is moving, when a body is sliding over a horizontal surface. Body is sliding over a horizontal surface, and we derive the expression for work done. Suppose there is a horizontal surface and a body of mass m is kept on the horizontal surface. So the weight of the body acting downward. Let the mass of the body is m be the mass of the body, then its weight acting vertically downward. And normal reaction acts opposite to the weight in upward direction. And normal reaction is represented by R. Suppose a force F is applied in horizontal direction. Suppose a force F is applied in forward direction, then force of friction acting on the body Fk. Force of friction, kinetic friction, Fk. Kinetic friction acts against the force, applied force. Now, after applying the force F, suppose the body displaces its position and body covers a distance of S. Body covers a certain distance, S meter. Now its weight mg is in downward direction, normal reaction is R, and body covers a distance S in horizontal direction. F is the force in forward direction and kinetic friction Fk in backward direction. So this was the initial position and this is the final position. After applying the force on a body of mass m kg, body displaces or body covers the distance s in forward direction. So we have to find the expression for work done when after applying a force on a body of mass m, body covers a distance of s meter in forward direction. So the work is done due to the force of friction. So expression for work done. Work done in moving a body. Work done in moving a body distance x, work done in moving a body, distance x, s. So work done equals to force into displacement, and force means frictional force because work is done due to the force of friction. So force into displacement, Fk into S. And we know that force of friction is given by mu into R. So Fk equals to mu into R into S. And mu K, kinetic coefficient of friction, mu K into R into S. And we know R is equals to mg. So mu K mg into S. This is the expression for work done when a body moves, when a body slides in forward direction and it covers a distance of S. So the expression for work done equals to mu K, coefficient of kinetic friction, mu K mg into S. So this was the first case. Work done when a body is sliding over a horizontal surface in forward direction. Now we discuss another case. And that is work done in moving a body up an inclined plane. Second case. Work done in moving a body up an inclined plane. Work done in moving a body up an inclined plane. So suppose there is an inclined plane. Plane is inclined at an angle of theta with the horizontal. This is the inclined plane. The plane is inclined at an angle of theta with the horizontal. And there is a body of mass m. And we have to find work done in moving a body up an inclined plane. Means body is moving in forward direction. So force F acting on the body in forward direction. Its weight acts in downward direction. Weight of the body mg always acts in downward direction. And the normal reaction acts perpendicular to the surface of the body. R is the normal reaction. And in a direction opposite to the force applied, the force of friction between the plane and the body. And this is kinetic force of friction, which is represented by Fk. Kinetic force of friction. Now produced this normal reaction. So if this angle is theta, then this angle also becomes theta, which we have discussed in previous video how it comes to theta by geometry. Now mg is inclined at an angle theta. Therefore, it must have two components. One is horizontal component and the other is vertical component. This is force of friction Fk. So the horizontal component mg is making an angle theta. So this component will be mg cos theta and this is mg sin theta. mg cos theta and mg sin theta, these are the two components of mg. Now we resolve these forces. So total in upward direction, the force is normal direction. So upward force equals to total downward force. In downward direction, the force acting is mg cos theta. So R equals to mg cos theta. R equals to mg cos theta. This is the first number equation. Now, along the direction of plane, the force acting in forward direction, the force is F, by which body is moving up on an inclined plane. And in a direction opposite to this force, there are two forces acting. One is the kinetic friction Fk and another is the mg sin theta. So the applied force F is equals to mg sin theta and plus Fk, kinetic friction. The direction of these two forces are same, therefore they will be added. So F, capital F equals to mg sin theta plus Fk, and Fk, force of friction, is written as mg sin theta plus Fk is equals to mu k into R. By formula we know that Fk equals to mu k into R. F equals to mu into R and mu equals to F by R. And R, we put the value of R from first number equation. So from first number equation, F equals to, from first put the value of R. Put the value of R. So F equals to mg sin theta plus mu k into R, and the value of R is mg cos theta. So plus mg cos theta. Now from both the terms, mg is common. So we take mg as common. So it remains sin theta plus mu k cos theta. So this is the expression for force acting on a body when the body is moving up an inclined plane. This is the expression for force. Suppose the body covers the distance S, then the work done equals to F into S, force into displacement. So work done equals to, the value for force is mg sin theta plus mu k cos theta and displacement S. So this is the expression for work done. In a work done in moving a body up an inclined plane. mg sin theta plus mu k cos theta into S. S is the displacement. So the case is body is moving up an inclined plane. The plane is inclined at an angle theta with the horizontal. So the horizontal force acting in forward direction, weight acting vertically downward direction, and normal reaction acts perpendicular to the surface. Perpendicular to the surface means 90 degree from the surface. Now produced normal reaction are in backward direction. So if this angle is theta, then by geometry this angle will become theta. So FG is inclined at an angle theta with the horizontal. So there must be two components of mg. One is mg cos theta, another is mg sin theta. And the kinetic friction acting in a direction opposite to the applied force, Fk. We resolve these forces, vertical force and horizontal force. So in vertical direction, the normal reaction acting upward R, and in downward direction, the opposite force is mg cos theta. So R equals to mg cos theta. Now in horizontal direction, along the direction of the motion of the plane, F equals to these two forces, mg sin theta and frictional force acting in backward direction, and these two have the same direction, so they will be added. F equals to mg sin theta plus Fk, and we know Fk equals to mu k into R, and the value of R we put from the first number equation, and then work done equals to force into displacement. We put the value of F. Now the third case, work done in moving down an inclined plane. Third case is work done in moving a body down an inclined plane. Work done in moving a body down an inclined plane. Work done in moving a body down an inclined plane. Plane is inclined at an angle theta with the horizontal, and there is a body of mass m. So its weight acting downward, mg, normal reaction acts perpendicular to the surface, normal reaction R. If this angle is theta, then this angle will also be theta by the geometry, and the body is going down, moving down. So the force acting in downward direction, applied force, the force by which body is moving down an inclined plane, and force of friction, kinetic force of friction acting in forward direction. So there must be two components of mg. One is mg cos theta, and another component lies on in the direction of the force F, and this component is mg sin theta. Now we resolve these two components. So R is equals to mg cos theta. R is equals to mg cos theta. R equals to mg cos theta. R acting in upward direction and mg cos theta is acting in vertically downward direction. and in horizontal direction, Fk acting in upward direction, mg sin theta and f in downward direction. So Fk is equals to f plus mg sin theta, f plus mg sin theta, and f is equals to Fk minus mg sin theta, and Fk is written as mu k into r. Fk is written as mu k into r. So mu k into r minus mg sin theta. Now put the value of r from first. Put the value of r from first number equation. So f equals to mu k into the value of r is mg cos theta and minus mg sin theta. From these two expressions, mg is common, so we get mu k cos theta minus sin theta. This is the expression for force, and the formula for work done. Work done equals to force into displacement. So mg into mu k cos theta minus sin theta, and displacement is s. So this is the work done when a body moving down an inclined plane. The body is moving down an inclined plane. So F force is acting in downward direction, weight acting vertically downward direction, and in upward direction, perpendicular to the plane, normal direction. And if this angle is theta, then this will be theta. There must be two components of mg cos theta and mg sin theta, and frictional force acting along the direction of the plane opposite to the direction of the force. Now we resolve these forces. So R equals to mg cos theta and Fk equals to mg sin theta plus capital F. And F is equals to Fk minus mg sin theta. We put the value of Fk mu k into R and put the value of R. So mu k mg cos theta minus mg sin theta. Mg is common, so we get mu k cos theta minus sin theta. Then we calculate the value of work done. Now the next we discuss acceleration of a body sliding down a rough inclined plane. Acceleration of a body sliding down. Acceleration of a body sliding down. Acceleration of a body sliding down a rough inclined plane. Sliding down a rough inclined plane. Acceleration of a body sliding down a rough inclined plane. There is a rough inclined plane. Plane is inclined at an angle of theta with the horizontal. So its weight acting downward, normal direction acting upward perpendicular to the surface. This angle will be theta. If this is theta, then this angle will also be theta. Body sliding down a rough inclined plane. So there must be two components of mg cos theta, and another is mg sin theta. And body is sliding down. So the force of friction acting in upward direction, kinetic force of friction Fk. Now body is moving in downward direction and force of friction acting in upward direction. Therefore the resultant force, the direction of the resultant force in forward direction, because body is moving in forward direction. So the resultant force F, let F be the resultant force and A be the acceleration produced. Let net force acting on the plane be F. Let net force acting on the plane be F. M be the mass of a body. And A be the acceleration produced. And A be the acceleration produced. So the net force acting by which the body is sliding down, and that net force is F. So F must be equals to mg sin theta minus Fk. F equals to mg sin theta minus Fk, because mg sin theta acting along the direction, along the plane, and Fk acting in opposite direction, and this force is greater because body is sliding down. So F equals to mg sin theta minus Fk, and from Newton's second law, resultant force F equals to mass into acceleration. Mg sin theta minus Fk is written as mu k into R, and R is equals to mg cos theta. R is equals to mg cos theta. So put the value of R in first number equation. Put the value of R in equation first. So we get M into A equals to mg sin theta minus mu k, and the value of R is mg cos theta. So MA equals to, from these two terms, mg is common. So it becomes sin theta minus mu k cos theta. M and M gets cancelled, and the expression for acceleration g sin theta minus mu k cos theta. Acceleration A equals to g into sin theta minus mu k cos theta. So this is the expression for the acceleration of a body sliding down a rough inclined plane. Then the acceleration on the body A equals to g into sin theta minus mu k cos theta.